This week, we're going to talk about extratropical storms, mid latitude lows and fronts, and basically the weather that involves our area. So, I thought I would just start by showing you this is a 48-hour forecast of 850 millibar temperatures and surface pressures and precipitation. Uh, what I want to show you is if you go back on this just a few frames here, I want you to watch. There's no low at all initially here on Sunday night. But notice there's a temperature gradient right in here. That's a warm front, or in this case, a warm front out here and a cold front here that's developing along the Gulf Stream of the east coast of the United States. And if you watch it, you can actually see, notice the low pressure beginning to develop right here. Isobars are kinking up, the lower pressure is down here. So you're winding up with weak low pressure right in here. And it's actually pulling the colder air and the warmer air closer together, creating a greater temperature contrast with time. And with that, it actually develops precipitation, uh, upwards of an inch or so down here in southeast Virginia and northeast North Carolina, right along the immediate coastline. So you can actually see here the birth of a very weak, but still a low pressure system. It's a much stronger one up here over Hudson Bay. Very strong temperature gradient up here just north of this area. So if you wanted to look at the upper levels, I'm showing you surface and 850 temperatures because I can really pick out the contrast in temperatures here. But let's take a look. Go back up one. And if I just look at 250 millibar winds and heights, and we'll go out to about the same time, 48 hours. I see a dip in the jet stream here. Jet stream's up here. Notice the fast flow from the west to the east across right along the Canadian-US border. But then right along the east coast, there's a very fast southerly jet. With that, we learned that left front and right rear quads and where the jet bends are the places for divergence. Right in this area, you would expect divergence then. That is the area where that low pressure is. So we can correlate looking at this that we're getting the divergence aloft, getting convergence and temperature contrast frontogenesis increasing. So we wind up with more and more low pressure here, right along the East Coast. One of the biggest influences is why the East Coast gets that is the Gulf Stream is right there. Now, notice up here, there's another jet. I'm not showing you far enough north to really see it, but there looks like there's a big upper level low right up in here by Hudson Bay and all. So that is correlating to the stronger low that's up there, which, remember in the planetary circulations, you learned that was around 60 degrees north. That's pretty close to where that is right now. So a lot of low pressures up in that area. Now, let's go and look now through some of the things you're going to learn about here. Minimize this and we'll bring up the PowerPoint here. And let's just look at this a minute and see what we can learn from some of this about the mid latitudes where we live. So weather systems of the mid latitudes. Uh, what systems shape our weather? Well, we just showed you where a low pressure system developed along the East Coast. And using just what you have learned so far, you could see where the divergence aloft helped the air to lift. That lifting air brought in moisture, increased the temperature contrast, and created a low pressure system, all producing precipitation in 48 hours right along the east coast of the United States. So, first observations. Many years ago, everybody wondered where the weather came from, what was going on. A guy by the name of Daniel Defoe proposed that storms generally track from west to east where we live. And then Ben Franklin observed also, hey, when I have an east wind or whatever, that doesn't mean the low's coming from there. He correlated that the winds did not represent where the low was moving from at the surface. And we've learned that they flow counterclockwise around low pressure systems and clockwise around highs. It doesn't translate very well when you're looking at surface. So the biggest key to understanding the weather in our area, we're kind of a transition zone. Think about it. The tropics, always warm and humid. Don't get cold fronts or warm fronts. Wonderful. If you like warm, humid weather, they're the place to go. Now, if you like cold weather all the time, you go up north in northern Alaska, parts of Greenland, all of that. Hardly ever get a frontal passage because it's always cold. Warm fronts don't necessarily come up there very much. Right between the two, where we live, is where the interest begins. So there are different types of air masses. We talked about air masses before. Air masses cover large areas. They may cover all of Canada or all the United States. They may cover huge mass of the Atlantic or the Pacific. But that air mass will all have fairly uniform temperatures and fairly uniform moisture. They form underneath high pressure systems because highs tend to develop in these areas, and they tend also to make the winds very slow. So the air actually takes on the characteristics of where they're over. So if I'm over Canada, Canada doesn't have a lot of water in it, but it gets pretty cold, especially in the wintertime, not getting a lot of sunshine, we've learned. So you wind up with a continental polar air mass. Some air masses even form up in Siberia and over the Arctic, called Arctic air masses. Now, desert Southwest. Well, it can get pretty hot down there, really, really dry. So you have a continental tropical. Notice the continental tends to imply low moisture because it forms over land. Now, we have some more maritime air masses. We have maritime tropical, which can form over the Gulf of Mexico, Southeast Atlantic, where the big Bermuda High is. Perfect examples of where, think about it, there's not much motion of the air out there. So what's it do? The Atlantic's pretty warm in that area. The air becomes warm, humid. You can also get maritime polar air masses. They affect places like Seattle, Washington, northern, southeastern Canada, southwestern Canada there and all. And they're also in the polar Atlantic as well. And they can come down along the east coast of the United States. They're moist, not as humid as the maritime tropical ones are, but they're humid and they're cold. The Atlantic can be fairly cold up in that area, so can the Pacific. So now that you've got the air masses defined, what we want to know about that is what's between them. And also these air masses will modify. One of the interesting things I wanted to point out is that as continental polar air masses come out of Canada and down across the United States, say you just had a major snowstorm come through, blanketed snow across Chicago, across Ohio, into West Virginia. Past that, no snow. It was all rain east of that area, we'll say. So as that continental polar air mass comes in, pushes across the Appalachian Mountains, it doesn't lose a lot of its coldness. It's still pretty cold. As it moves on, winds up going across the Appalachians. It's sinking, that's first, and there's no snow. So there's two things going on here. Your temperature is warming from the sinking, and the underlying surface is warmer than where all the snow was at. So you wind up heating the bottom of the air mass, which makes it more unstable. So it's mixing out more. What do you wind up with? A warmer air mass. The same thing does not happen as frequently or as fast with maritime tropical air masses. When they move in, maritime tropical air masses are already moist, They're warm, so they move over the land. Wow, that land is colder than they are, so it actually stabilizes the air mass so that the modification doesn't occur as fast. And this is really, really key in the wintertime. So fronts are right where these air masses change, and they can be pretty narrow. They can be maybe up to 100 kilometers wide sometimes, and other times they're only like 20 or 30 miles. And when you think about the front, it's how fast does the air transition from warm to cold or cold to warm, is how narrow that front is. So right along that boundary, you're going to get a change in humidity and a change in temperature. All right, we've learned that colder air is the denser air. So if colder air wants to move south, it's going to move south. It's going to push the warm out of the way. If the cold air wants to go back to the north, warm air is going to come in to take its place. So the cold air is always the influencer of where fronts move. So here is a stationary front. This front's not moving anywhere. What happens is that maybe the wind flow aloft is set up, or maybe, oh, say I have a stationary front that forms along the Appalachian Mountains where winds come in off the water from the Atlantic and are pushing into the mountains. They don't cross the mountains, so you wind up with cooler air on the east side of the mountains, warmer air on the west side of the mountains, and what you get is a lot of cloud cover east of the mountains where the warm air is rising up and over there, and lifting motion from the mountains is helping to keep it there, but that front is not moving, it's stationary. So you wind up with bad weather for days on the east side of the Appalachians and wonderful weather on the west side. Warm fronts. Warm fronts mean that the cold air to the north is moving away. So that allows the warm air to come up. As it comes up, if you ever knew that a warm front was coming, you can watch and see the cirrus clouds develop over you. They get thicker, then they begin to lower to alto stratus, and they're almost always some form of stratus clouds, stratocumulus clouds, whatever, till eventually they get down to nimbostratus and precipitation starts occurring. If, interestingly, on the warm side, maybe on the cold side, excuse me, as it's coming north, maybe there's a area of snowfall. Maybe that'll change to freezing rain and eventually just to rain. When I look at precipitation, sometimes when I've had to drive in winter weather, one of the things I would try to watch for is where these warm fronts were and which section of that cold air mass I might be in. One time we attended a hockey game in Pittsburgh. We were driving from State College, Pennsylvania to that game. We knew there was a warm front coming up, and there was actually a pretty strong low going to our west. So we knew that at State College, as we were driving, we were going to start out in some form of snow. And if we stayed to the north, we'd probably stay in snow or icy conditions. We decided that we wanted to get out of that as quick as possible. So we drove to the south and took a more southern route. And it paid off big time because north of that area, some areas had 5, 6, 8 inches of snow while we had mainly rain. And we drove in rain basically all the way into Pittsburgh. So understanding where these fronts are can make a huge difference on what kind of precipitation you're going to deal with. Cold fronts, remember, cold air is much denser, so the slope of a cold front is going to tend to push the warm air up very quickly. So you're going to find the temperature contrast also changes very, very quickly along a cold front. Much slower maybe along a warm front. But along a cold front, as it's pushing in, you might go from, oh, it's 70 degrees. 15 minutes later, it's 50 degrees or 40 degrees. So these fronts are very tight. They tend to push the air straight up, which that kind of lifting and all with warm air aloft and coming in, you'll wind up with more thunderstorms. Fronts can move in any direction, but I was talking about that stationary front that comes along the Appalachians sometimes. Many times that front slips down on the east side of the Appalachians and just gradually bows in to where it just messes everything up on the east side of the Appalachians, makes it colder and more miserable on the west side. Just wonderful weather. Occluded fronts. They're in the end stage of an extratropical cyclone. They occur at the very end. So let's look at them a minute. What happens is cold air is moving along, and it may be moving faster than the warm air is out ahead of it. So you have this low pressure system, and what happens is the cold front catches up to that nice warm air, and because the cold air is denser, it starts lifting it up. And you wind up out ahead of that warm front somewhere is cooler air, but you wind up never quite catching that into that air mass as much, but you push the warm air aloft. That's a cold type of occlusion. Sometimes out in the Pacific more, you might get cool air coming in, but it's even colder out ahead of it. So you wind up still pushing the warm air aloft. So you have cool air slowly pushing into the colder air that's out ahead of it. That's a warm type of occlusion. These only occur in the near the end cycle of an extratropical cyclone. So we've talked about fronts. Fronts can grow stronger. I showed you an example of that at the very beginning, that front developing along the east coast of the United States there, growing stronger. It's because the air is converging in. It pulls in the cold air from the west and the warm air from the east, and you wind up getting stronger and stronger fronts. Sometimes you wind up the opposite. Air is getting pushed apart. The front is going to weaken. So, a little bit about extratropical cyclones. First off, they're not tropical. So, that monster storm I showed you going through Jamaica, that major storm was not an extratropical cyclone. So, extratropical cyclones are bigger in diameter than tropical. Wind speeds tend to be lower, and they tend to occur mainly in December through March in the United States, but earlier than that too. We've just seen one forming on the East Coast now. And they tend to occur about every 3 days. They're going to move around through your area. So yes, you all have experienced extratropical cyclones. And they last about 3 to 5 days. So initially, just like I was showing you on the East Coast, you wind up with a cold front and a warm front coming together. Temperature contrast is increasing, and you get low pressure systems. Sometimes that's about all you ever get, just that weak low, and it moves on out. But sometimes it gets more intense. Because it's getting more intense and deepening, it's pulling in the warm air from the east, cold air from the west, lows wrapping up. So you wind up with a more intense system. Also, notice the cloud cover. You get a lot of clouds sometimes at the weak lows and rain. You have pretty heavy rain sometimes. But in this one, notice how the clouds are more and more to the west. Actually, one of the things meteorologists can look at with time is how the evolution of the clouds are going. We can actually pinpoint lows by looking at where the clouds are shaped like this, and detect whether the lows are deepening or not by seeing how the clouds continue to wrap around it all. And now, here we did see, at this point, we have an occluded front right by the low where the cold air has wrapped into the warm air and pushed the warm air aloft, and eventually more and more. But notice how it really is a comma shape to it. That's an extratropical cyclone. They pass across the United States frequently. Sometimes we can have 3 or 4 in the country at the same time. Here you can see that strong hook echo. Here's the cold front coming down, warm front out here, and there's your low. So there's another model. The idea is to see how air masses are moving in the front. So let's take a look at that. We have a cold conveyor and a dry conveyor belt. All right. So front's going to pull in air from the northwest. As it's doing that, that air is sinking down and drying, coming across this area behind the low. Sinking air is behind the low, rising air is ahead of it. So you wind up with drier and drier air. Now, from the east, you got a warm conveyor belt, and you also have a secondary cold conveyor belt. That cold conveyor belt is what forms the comma head. Comes in from the east, off the Atlantic or off the Pacific, and lifts up and over that low pressure. Remember, you got very strong divergence up here. So the warm, cooler air, cool, moist air, being lifted, getting it more and more saturated, precipitation, and you're pulling it west to form that comma head, then it wraps back to the east. So by understanding a little bit about these conveyor belts, you can understand where the warm air is coming up, providing the moisture, cold air is coming down, keeping the moisture snowfall, maybe helping to generate more of a temperature contrast, which helps fuel the system. So all of it works together. And these cyclones have different weather in different sectors. And it doesn't take much to be off on a forecast. And you need to be accurate, very accurate with the forecast on where the low is going to be if I want to give you the best weather forecast. Because here is cold air across to the north and northwest of the low, warm air to the east, and best to the southeast. You can see the cold and warm sectors. So if the low is moving in this direction, and I live in here, I am assuming right now that that low is going to pass to my northwest. If it is, then I'm going to be in drizzle, light rain. North of me, however, probably going to be getting snow. Now, oh, I was off. That low is going to pass across southern Michigan. Well, in that case, that area I thought was going to be rain just became all snow, maybe even some freezing rain in there. Changes the forecast tremendously. Notice pressure falling, low is moving towards an area, pressure rising behind the low. One of the greatest ways to see how the low is moving in real time is to look at the pressure falls and see if you can track where the pressure is rising and falling. You can point where the low is moving towards. Lows can come out in all kinds of different directions. The East Coast one, which I was just showing you there, starts along the coast. Sometimes it goes right out to sea. Other times it'll move up into New England. So there are a lot of different areas that lows can form. They can form in the Gulf of Mexico. They can many, many times form coming off Colorado into the plains. And you get the Alberta lows. Alberta lows are just very fast moving. They tend to run right across the northernmost part of the United States. Notice there's no moisture around for them to get, so they wind up not having much moisture. They move quickly. And here is just typical Chicago. If it passed on the warm side or the cold side, you can see the different changes in wind direction and all of that correspond to it. Winter storms, any storm that has snow or freezing precipitation is a winter storm. So with that, there's another category of winter storms called a blizzard. A blizzard requires at least 35 miles an hour or greater of wind and visibility less than a quarter mile. So if you have a nice gentle snowfall coming out your window, but there's not much wind, that is not a blizzard. It might produce feet of snow, but it's not a blizzard. So I just wanted to emphasize that. And here you can see the typical winter storm. Again, depending on where that low goes can make a huge difference in what kind of weather you have. You only have to be off by 50, 60 miles. Extratropical systems are cold core. That means if you go up in the atmosphere, like you noticed when I showed you 300 millibars, that was a pretty intense low at 300 millibars there compared to the surface, which was relatively weak. That is a cold core system. Remember, in cold weather, the pressure will drop much faster in the vertical than in warmth. And here was kind of what you were seeing with the deep low and the actual surface low out ahead of it. Warm core. Warm core can be tropical, like we just had in the hurricane, like Melissa, or it could be tropical, where the thermal lows that form and generate the North American monsoon are warm core systems. Anticyclones are good weather. They tend to have subsiding air, nice sunny skies. I'm under one right now here at my house. I think you all are as well, many places. They can be cold, very strong cold air, or they can be the warm, nice, beautiful, warm weather. There are other wind circulations that occur in the mid latitudes. One is a sea breeze, or if you're up in the Great Lakes, a lake breeze. And then it can even be a river breeze sometimes. What it we talked about this last week when you were talking about winds, how the winds reach the surface coming from the water and they start slowing and convergence begins to occur. The reason they're coming from the water is, well, the land's heating up. Oh, the air's rising over the land because it's got more unstable, sinking over the water because it's got more stable. You wind up with a circulation. And then the convergence begins to take effect, and you wind up maybe with some thunderstorms in here. Land breeze, just the opposite. Valley breeze. Valley breezes tend to occur during the daytime. So what happens is the slopes heat up, sun's shining on them, pushing the air up, and then sinks back down into the middle of the valley, making more clouds along the slopes, less clouds in the valley. Nighttime, remember, cold air drains. You get the cooling on the slopes, it all drains down into the bottom of the valley. That can impact pilots tremendously in the Rocky Mountains. These kind of winds, when they come down the slope, are Chinook winds, and they can make the atmosphere more stable, dry out the air, because all the precipitation fell on the west side of it. Uh, I am sure none of you remember an Olympics that occurred in Calgary many years ago. Calgary has a tremendous amount of snowfall typically, but they're right on the edge of the Rocky Mountains. And almost half the Olympics, they had a Chinook wind. So they kept trying to find ways of making snowfall because the wind was coming down off the Rockies into that area. It would warm it, and it would literally eat the snow that was on the ground. Santa Ana is another form of Chinook winds. What happens is you wind up with high pressure out over Nevada, out over the Rockies, well, in their case, the Sierra Nevadas. And that high pressure is cool. And so the gravity begins to initiate a flow down on the west side of the mountains here. And when that gravity pulls it down, it's sinking. So sinking down the slope, it's increasing in speed. It's getting hotter as it goes, which means it's losing moisture that it had, getting drier. Winds are increasing, so you wind up coming into Los Angeles, San Diego, Santa Barbara, that area, all of it with a very dry, hot wind. And here you can see the classic example of that, where you have the thermal low here, but a huge high pressure to the north and into that area. Katabatic winds can occur on glaciers and all. They're also known as Mistral and Bora winds. They don't tend to have a lot of speed, but they do come down the cold slopes that are there. And in the deserts, there can also be some wind systems as well. Dust devils, classic example of a very small wind system. Hubbobs form in our desert southwest or out near in the deserts in Sahara and other areas as well. So hope you got a little bit out of this. I know I talked too long again. Let me know if you have any questions.